confidence interval for a population proportion. So we've dealt with only counts up to this point. Now we're going to look at proportions. So we draw an SRS, simple random sample of size n from a large population. With an unknown proportion P of success. So we don't know the population proportion. We won't know the population proportion, but we can get a sample and a p hat, sample proportion. We have to check our conditions. SRS has to be an SRS. We have to have independence. If they're talking about subjects, they need to be independent. And normal. Norm. Since we're talking about proportions, the central limit theorem doesn't come into play here. We saw something like this in chapter 9, where n times p has to be greater than or equal to 10, but we don't know p. So for this, it's going to be n times p hat has to be greater than or equal to 10, and both have to be true. N times 1 minus p hat has to be greater than or equal to 10. There's one other thing to consider. Our sample size can't be overly large either. Remember, we had something like the sample, the population has to be larger. Not P, sorry. Population size would be big N. Population has to be greater than or equal to 10 times little n, our sample. So be careful, that'll come up and get you. So all of this has to apply. And then we have our interval formula. Why I'm dotting my U's. It's Monday. U's are supposed to be dotted on Monday, right? Interval formula, p hat, plus or minus z star. So we're back to z. And times the square root of p hat times 1 minus p hat over n. Now, a mistake I've seen a time or two is this radical covers the whole fraction. I've seen a few folks take the square root of the p hat times 1 minus p hat, take the square root at that point, and then divide by n. You want to make sure that n is part of the radical. Okay. All right, and this part right here is, can anybody identify that part? The middle, plus and minus. It is the confidence interval, that's true, but that part, this part specifically, is the margin of error. And the standard error SE is that square rooty part. P hat times 1 minus P hat over N. Okay. So with the Z star, that's your margin of error. I call that the standard deviation adjusted for sample size is your standard error. Now you might be asked to calculate a sample size for a desired margin of error. That's going to be the Z star times square root of P hat times 1 minus P hat over N is less than or equal to the desired margin of error. So this is what you would have a desired margin of error, and you'd be looking to solve for N in this case. And just as a quick drawing of what this looks like, P hat is your middle, and your minus some margin of error and plus some margin of error. Kind of cramming this in, trying to get it into one page, but that's because I write big. So when we answer a question with a proportion, we have to change our phrasing just slightly. So we're going to say, it's mostly the same, we're going to say we are some blank % confident the true, it's not mean, it's proportion now, of, and then you add some content here, or context, is between blank and blank %. If you're writing it in % form, make sure you put the %. If you're putting it in decimal form, I don't think you don't need to put %. That would be contradictory. So the other day I said, when you're making a page of notes, it might be wise to put how you phrase this down. This is probably not a bad idea to add that, unless you can keep it straight, your means and your proportions. Right? So we're dealing with counts and proportions now. Everything we've done up to this point has been counts. It's very easy to do a proportion problem and then say the true mean of and lose a point on that, and I don't want you to do that. Okay, so be really careful about that. All right, shall we look at a problem? Okay, let's do that. On page 672, I'm going to look at 1051. Let's see, 672, let me get to that myself. And it's talking about job applicants lying. You think job applicants ever lie? Nah, never. Humans don't lie. What reason would they have to lie about a job application? So I certainly have, in my previous past, hired and fired a few people with other jobs that I've had. And I've had one instance in particular where a fella told me all the great things that he knew how to do, and when he got out into the real world and had to actually do them, he didn't. So it does definitely happen. The one that bothered me the most, and I don't know why this bothered me, but when I was in college, I was dating a girl, and her sister was a little older than her. She was married, and the sister's husband was working as a rep for some auto parts store or some auto parts company of some sort or another. And he joked that he didn't have a degree. The job required a degree, and he'd been to college. I guess he was, a few classes shy of a degree, but he told him he had a degree, and they never questioned it. So he's doing this job, and it's like my head would explode if I thought that all it would take is somebody to look back into my past to find out that I didn't have a degree that I said I had. Because, I mean, you're talking about your and your family's income, right? They were fairly young at the time, but I always wonder how that ended up playing out for him. It might not have ever caught up to him, but it's kind of like breaking out of prison and not getting caught, right? But you're always worried that somebody's going to catch you. So, I don't know. Anyway, so in this problem, this company does a check on 84 of their applicants. 84 are checked. And 15 lied of those 84. So N is 84. The 15 is X. I write those numbers down specifically to help you with the calculation. So A says, what's P hat? Well, P hat is going to be this X over N. Success? Success, they've cheated. 15 lied out of 84, which works out to be about 18%. So P hat is about 18%. And it wants us to find the standard error. Well, that's the standard deviation corrected for sample size. So that's going to be the square root P hat times 1 minus P hat divided by N, which is, I have a calculation of about 0.042. Might want to double check me on that, but I think it's right. 0.042. You got it? Good. Okay. Well, either we're both wrong or we're both right, yeah? Okay. All right, so B asks us to make a 90% confidence interval for this. My question to you would be, do you think 90% is appropriate for this situation? Your company looking at applicants that have lied to you. Do you think a 90% confidence, or would you think more or less? So here's my thought on this, if you're a little unsure. I think 90% is appropriate here because the company is looking at their own internal information. They're not necessarily using this confidence interval to go out and fire people or anything like that. However, I would have to guess that these 15 people are probably out of luck when it comes to getting a job with this company. Does that make sense? So they're just trying to say, at any point, how many would we expect to lie to us? So I think the 90% actually does work okay here. It does say, consider the data to be a random sample. So let's check conditions here. SRS, that's given. Independent, are you willing to assume that each applicant is independent? I'm thinking probably, yeah. Assume applicants are independent. Normal. Well, I've got 84 people that we're looking at. A p-hat value of about 18% are liars. Is that number greater than or equal to 10 is the first check. I think that's about 15%, right? It's about 15, so we're good there. And 84 times 1 minus 0.18 is definitely bigger than 10. That's going to be 70 or 82% of 84. It's definitely bigger than 10. So we're good for the normal. What's the other thing we want to consider? Is the population bigger than 10 times the sample size? You think it's reasonable to think that there's more than, what, 840 people that would be potential applicants for a job? Probably. If you've got as many as 84, so I think we're good on the other. I'm not going to write it down, but I think we're good on the other as well. Okay, so p-hat plus or minus z star, this is the formula we're going to use, times the square root of p-hat times 1 minus p-hat all over n. If there was anything I liked about this formula, it was this. There's only two numbers that I really had to remember, p-hat and n. You only needed two. So this is going to be 0.18 plus or minus 1.645. Now, something I told the other class that I think is wise. On your table A, now you can't do this for the AP test, but you could memorize it and write it in as soon as you got in. I actually put these values on my table A. That way I don't have to go looking for it. So 90%, 1.645 times this 0.18 times 1 minus 0.18 all over 84. And we already have a value for that. We can kind of plug that in if you want. So I'm going to go ahead and go to calculator here. 0.18 minus 1.645 times square root. Oops, I probably don't need that there. 0.8 times 0.82, that's 1 minus 0.18, divided by 84. So I get that this is 0.1112 0.249 about. So we're 90% confident that the true proportion of people who lie on their application about their education is somewhere between about 11% and 25%. So that's how I'm going to answer that. So we are 90% confident the true proportion of, excuse me, I'm going to keep this simple and just say liars, but on an AP test I would say proportion of people who've lied on about their education or something like that, of liars, is between, although you'd probably get away with that just fine. If you move the decimal and turn this into a percent, you want to put the percent signs there. If you just left it as the decimal form, I think that's perfectly fine. They'll know that it's a percent and that it hasn't been converted. Okay, so what's the shortcut? So here's what's going on. Our p hat is about 18%. We're plus and minus a margin of error to about 25% almost, 0.249 and 0.111. So we are 90% confident that the true proportion of liars is between about 11% and 25%. Everybody good with that? Give or take. Okay, so in the calculator, let's double check our numbers. If you go to Stat, Tests, we want the one prop z interval. So, oops, not that. I didn't want that. Stat, tests. One prop z interval is down a little ways. It's A. At least it is on mine. One prop z int. There's only two things it asks for. Well, three things. It asks for the x and the n. So it doesn't ask you to calculate p hat. It does it for you. 15 people lied out of 84 that were checked. Confidence interval 95. Let's see, I think we need 90%, right? Yeah, we did a 90% confidence interval. Calculate, and there we go. So pretty close to our 11%, to our 25% here. The numbers are a little bit different simply because we did some rounding that the calculator didn't do so much of. Our p hat value of about 18% and n equals 84. Pretty simple, huh? The trick is knowing when and what this stuff means, right? So I haven't followed up on it, but just a potential for this kind of math. A friend of mine's cousin does analytics for Google, and we were at a Christmas party this December together, and my son made a comment to him. I don't even know how it came up, but that I teach statistics. And this guy approaches me and he says, I don't know anything about statistics, but I know a lot about programming, but I'm doing this Google thing and I need some help with statistics. Are you interested? Google pays $175 an hour. He said, you'd have to work underneath me because you're not, Google certified or whatever. I guess I suppose I could get Google certified. But he says, I'd pay you $125 an hour for every hour that we can build a Google. That's pretty good stuff, right? I probably need to follow up on that. Anyway, yeah, there's opportunities out there.